So here we're going to take a look at kind of a connection between linear combinations and then solutions to a linear system and the corresponding homogeneous system. So first we'll start off, let's say here we have a linear, this is an augmented matrix, right? So we have here the coefficient matrix would be this part here, A, and then this part is our constant vector B. Right, and now let's take a look at a theorem in our textbook here. So we're going to look here at theorem SLC. So solutions to linear systems are linear combinations. So now we're going to start thinking of the solutions as just a linear combination of the columns of our coefficient matrix. Right, so here just reading this theorem, solutions to linear systems are linear combinations. So denote the columns of the M by N matrix A as the vectors A1, A2, A3 up to AN. Then X, element of C to the N, is a solution to the linear system LSA with a constant vector B, if and only if, right? So again, that strong relationship, right? Almost like a definition of what it means to be a solution. If B equals the linear combination of the columns of A formed with the entries of X. So written in this form, right? Again, the entries, right? Again, be comfortable with the notation, what it means, right? These A sub 1, A sub 2, etc., those are column vectors, right along with B. B is a column vector. And these X in brackets corresponds to a scalar, right? The scalar comes from the elements in the column vector X. All right, now let's kind of decipher, instead of going through the proof, let's just decipher this notation here, right, with our example here that I have illustrated here. Okay, so if we think of here as our matrix A, right, so the linear system described here by A, B, right, our B is this vector 8, negative 12, 4, right, and here is our matrix A. Now those column vectors, A1, A1, 2, etc., are these vectors here that are made up by these columns, A4. Okay, so those are those column vectors, right? A1 is this vector here, right? A2 is the next column, A3 is the next column, etc. Right? Now let's say that I knew that the solution to this system was a solution, I should say, is 4, 0, 0, 0. Okay, so what that theorem is telling me is that, okay, well, I have my column vector B 8, negative 12, 4, right? So that can be written as the column vectors of the coefficient matrix. So lining up all these column vectors here, we have that here. So A1, so we'll have 4 times A1, which is 2, negative 3, 1, plus 0 times A2, 1, 4, 1, plus 0 times 7, negative 5, 4, plus 0 times the column negative 7, negative 6, negative 5. Okay, and we see if this is a solution, then I can write the solution as a linear combination where these scalars from an A1, A2, A3 come from that solution vector here. And you can see, just to confirm, right, these go to 0. If you multiply that through by 4, we do in fact get 4 times 2 is 8. 4 4 times negative 3 is negative 12, and 4 times 1 is 4. So we see that that checks out. And I can do that for any solution, right? So even if it has an infinite number of solutions, you find one of those solutions and you can write it as this linear combination of the columns of the coefficient matrix. All right, now going a step further here, right, to end this section here. Let's see here, let's bring up our last theorem here. Okay. Okay, here we go. All right, so our theorem here is a theorem PS-PHS. So it means a particular solution plus the homogeneous solution, right? So it says that suppose that W is one solution to the linear system of equations, LSAB. Then Y is a solution to LSAB if and only if Y can be written as W, that particular solution, plus Z for some vector Z that is an element of the null space of A. All right. Okay. And again, here, this is if there is the null space only contains the zero vector, right? We only have a unique solution. So Y would be equal to W, right? But in the case where the null space is not empty, then all solutions would all have this form where Z could be any vector in the null space. And that would also be a solution. All right. So again, right, here's a excuse me, a theorem based on the column vector, and then applying the what it means to be a solution of a system. But let's take a look at our example that we got going here. So as it turns out here, if we take a look at this system, right? So again, still working off this system here, right? Where we have in 4 variables, right? We have 3 equations, right? Linear system with this constant vector AB. Now, let's say that I take that system and I put it in reduced row echelon form, right? As it turns out, this is the system that we worked on in the previous video. So it reduced row echelon form to this quantity here, to this matrix here. -3, 0, and then this is 0, 0, 0, 0, 0. Okay. All right. Okay, and then from here, we saw that I could write this solution here. Right, so I could saw that my solution vector was of this form. Okay. All right. Yeah, and we could see here if we simply look at just the coefficient matrix. So in other words, we kind of eliminate here that constant vector and think of just the corresponding homogeneous system, or excuse me, the homogeneous system, right? Well, I would still get this to reduce row echelon form to this matrix here, right? So here what I'm saying is, let's say I only look at the homogeneous part of this system, then that would reduce to the same matrix except without that last column, right? Or the last column is just populated with zeros if we're looking at a homogeneous system. Okay, so this is the non-augmented part, right? If we just think of the homogeneous system, well, I can describe the null space in this manner, right? You just get that part right there, the ones that have the parameters, Right, so as it turns out, the null space of A here is equal to the linear combination of S2, 3, 0, 1 plus T, negative 3, negative 1, 1, 0, where S and T are real numbers. All right. Okay, and we could see that the theorem here is illustrated in this form of a solution, right? Where we have W to be a solution here, and then the other part of the solution, S and T, is just an element of the null space. All right, so now we can see here that, and this will hold for any linear system here, where we have what's called a particular solution, right? That W is one particular solution. And then the, give me a second here. We have the particular solution represented by W, right? A solution of the system. And then Z is in a null space. And again, another way to interpret that, if it's in a null space, that means it's a solution to the corresponding homogeneous system. So I can write solutions to any linear system in this manner, right? Depending on what the null space looks like, right? Then that would affect how our solution looks like.